Yeah, I think more people will be joining in. But yeah, maybe we
Okay,
can start.
it started.
Okay, thank you. Okay, and hello everybody. Welcome to my presentation. Thank you for joining in. So as you can see by the title, this presentation is about 3D printing. So I was in charge of designing and printing the actual Hack9 cases that will be used for the hackathon. And I would just like to say that it was really satisfying and it was a pleasure to work with the organization team because this allowed me to help the hackathon and help the company by utilizing some of my skills in a creative way. So I started tinkering with 3D modeling maybe about 2 years ago. And yeah, it was really satisfying for me in order to help this way, since this is kind of also my hobby. So I'm happy with what we've created. That the design that you will see is not perfect. It could always be better, and during the presentation I will walk you through some of the steps I took and the decisions that I made during while designing this case. But yeah, this is what we came up with, and for now it looks good enough. But yeah, of course, it can always be better. Okay, so let's get into with the actual first slide. Just a second. So yesterday, Milos Puic gave a really good presentation about the actual hardware that's inside the cases. So again, we have the humidity and temperature sensor. That's the blue one on the left. Um, Sometimes I might refer to that one as the medium size sensor. The largest one is the PM sensor, and the smallest one is the pressure and temperature sensor. And also in the back, we have the Raspberry Pi. That's the brains of the operation. Okay, on the next slide, here we have all the locations where the boxes will live. Some of them are already in their intended offices. So the idea is to have one in each office so we can gather as much data, as much relevant data as possible so that the participants can use that data during the hackathon. And this is planned to be like an ongoing thing. The boxes and the sensors should work in the long run so we can check what the situation is in other countries and so on and get maybe valuable data from that. So like the tickets that we're all very familiar with, everything started with the requirements. So on the left is one of the first rough sketches that we made when we were talking about the design. And actually, a funny story how I came to be in the organization team is because of my hobby of 3D printing, I have a pencil case that was 3D printed on my desk. And Miro noticed that, and then we got talking, and then we had the idea for me to actually join in and actually build and design those cases. So this is what we came up with during our first initial meeting when we talked about the design. It's very rough and ugly, but it was a baseline for what was to come. So the requirements were that it has to be weatherproof. That means that it has to survive outdoors. And that's why I chose to use PETG plastic. That is the second most common type of plastic that's used in 3D printing. And the other one is PLA, but PETG or PETG is better for the outdoors because it has a higher melting temperature, and it can so it can sustain sunlight and not damage itself and not melt. So that was a no-brainer and an instant decision. Since I know the properties of both plastics, since I use both, I knew that we would be using PETG for this application. The next one is that it should be waterproof. Since it houses electronics and electronics and water don't mix very well, it was important to have the box waterproof, but also since it's using air, since it's an air quality sensor, right? It has to have access to air, so it can't be a tight box. and that means that it has to have openings for air to actually come in, but it has to be designed in such a way that it does not allow water to come in. So during the design process, I was constantly thinking about that, and then you will see how the design came about with that in mind. One thing I thought of that it has to be bug proof. So outdoors, we don't just have air, dust, water, and so on. We also have bugs that like to crawl into spaces. And so we had the idea to put a screen, a window screen, or a bug screen. So it's basically like a net that we just glued in place in the box so flies can come in and so on. Then, of course, it has to house all the electronics, which means I had to get the dimensions of each individual sensor using basically calipers, writing it down, and just implementing that into the design. And of course, it had to be Levi 9 branded. And the approach I took was to create the box separately and create the letters separately. So this is a prototype. I'll get to that. And then just glue the letters into place. I'll talk more about that, why I chose that approach. Next, it has to be mounted to a wall. So all of the boxes have a wall mount that the boxes slide into. Let me just turn off this filter so you can see it better. Apply background effects. Apply. Okay. So yeah, this is the wall mount that goes on a wall. We also made a version for zip ties, so it can be connected with a zip tie, so you don't need to drill a wall. So those are these bits. Then it needs to suck in air, which is why the holes come in. And of course, it has to be optimized. It has to be an optimized design for 3D printing. I'll get to that later. Also, it needs to be very durable in order to survive long, and I wanted it to be as simple as possible to not over-engineer it and just we're basically building a box that holds electronics. So I was constantly keeping that in mind. Okay, and now we're moving into the demo part of this presentation. So computer-aided design, the CAD software of my choice is Autodesk Fusion 360. It's a very beautiful program to work with. If you're familiar with SolidWorks, it's just like that, but in my opinion, a more user-friendly interface and yeah, very easy to pick up. And it's actually free for hobbyists. And also, if you have access to somebody who's still in university, it's free for students as well. And actually, students get the full package, which includes some simulations, renderings, mesh tools, and of course, the basic CAD tools. So without further ado, I'll move into the Fusion 360 program. I think you see it, right? Okay, so this is the finished box basically. And in the bottom here, you see a timeline. So it's a very long timeline. Let me just scroll through it. So these are all the steps that I took in order to get to the final design. And I thought that we could maybe go more or less step by step. I will be skipping some stuff. So let's see how it was actually made. I'll go to the beginning. And then this is just defining the tools. I imported the Raspberry Pi model that we will be using. This is important so we have the right dimensions for the holes. So I first started with the Raspberry Pi. Since I knew the model, I just downloaded a model from the internet, positioned it into place. Okay, the first sketch I made was the base. So that's the absolute bottom of the case. And let's see what I did from there. Yeah, just basically extracted it. And this is what we started off with. Next, it was really simple to just extrude the back of this to the desired dimensions. Next, we made another sketch. Let me just explain this one. So I just made an outline on this border. Just hide it. And I extruded the outline. So if you can see, I decided to have these like sharp edges with water in mind, so water could slide off, and with this one as well. So it's not a clear edge. My thinking was it would be better for waterproofing it. And these kind of teeth, as I call them, are also in order to hold the other part of the case in place, and also better for waterproofing it. The next one is another sketch. I basically did the same thing here, added another tooth here on the top. Okay. Now we extracted from the bottom, and this allowed me to create the front piece. And next I just cut it out like so. And now we just have a hollow box, and you can see where the two pieces meet here. This is a sliced version of it. Let me just turn that off. Next, we started off with the features. Oops, just a second. Let me just show this. So this is kind of a mess. Since this took a lot of measuring from the sensors, and I sketched this so I can extrude it one by one, and I'll go through this quickly so you can see what I mean. Oh yeah, and we cut a hole here so the Raspberry Pi has power to the board. So now I gradually just started extruding this until I got the desired shape that I wanted. And let me just go through the rest, since I think you have the idea now. Okay. So yeah, these are basically the things that hold the three sensors in place. So this one is for the big PM sensor. And if you notice this here, just a second, let me just close this. This edging out is for zip ties to hold the sensor in place. So one goes around here into the back, and the other goes from here to here. And basically that secures the sensor in place. It's a quick and easy solution to use zip ties since they're strong, and then the sensor is not going anywhere. The next one here, the small pressure sensor has just these two holes, which you can just put screws through them. We don't have 3D models of the sensors themselves since that wasn't necessary. I just needed their dimensions. So yeah, you just put the holes here, and that holds the pressure sensor in place. This one has two holes. That's for the humidity sensor. And the reason it has two holes is so that it can be oriented in either way. So either right way up or upside down. So yeah, you can do whatever configuration you want. And of course, the sensors are elevated from the floor of again for water purposes. So yeah, it doesn't get to the sensors. They're in the air. No chance of them getting wet. And the same idea is for the Raspberry Pi. If I turn it to the right here, the Raspberry Pi is basically above the ground, and it's connected to the wall here. But I implemented that a bit later. Here you can see the first hole that was made, and if I skip to the next part, of course I made 9 holes because Levi 9. So yeah, since the since the PM sensor sucks in air, it was important for it to be elevated right above these holes here, so it has easy access. Yeah, I think that's all for these holes. Just see what was next. Yeah, so here I drew, let me just show this. So this is for the nuts. I just made a cut here because I measured the nuts that will be used to hold the Raspberry Pi in place. Just see what else we have here. It's a big timeline. Oh, I think I started working on the front. Yeah, that's why it wasn't showing up. So yeah, the next thing was working on the front. Let me just go back a few steps. So I think we went through three prototypes, and we found out that we needed more holes for ventilation so that the box doesn't get really cooled. So I went for this design. Let me just see front. Let me just cut it so you have a better idea. Okay, that's fine. So why I went with this design, again, with water in mind, let's say it rains and then rain comes down, it can't get in here because this is at an angle. And it's good enough for air to come in and cool all the sensors sufficiently and the Raspberry Pi. Let me just skip a few steps. I'll get to these later. Let's just see a few more renderings. I don't think I have to go through all of it. Okay, so now you see these things here. They're not they're not cut all the way through. So I designed this. Let me just demonstrate on this prototype here. So I designed this in order to have for us to have an easy way to open the boxes. You just put your index fingers on the side here and your thumbs on the back, and you just push up with your index fingers and it opens the box easily. And I'm happy with the end result because it's still strong enough. If I just hold it by one side, the box won't open. It's a nice seal, but also this allows us to easily open it when needed. Let me just continue here. Side. Okay, now we get into the letter parts. Don't remember. Yeah, here, let me just go back. So yeah, I imported our font and I designed it in this way. So I mentioned that I went for this option to just put letters to glue them in place rather than just printing them out. Basically, because I only can print one color at a time. I can't print multiple colors because I don't have that kind of printer. So that's why I went for this approach to just glue the letters in place. And of course, we made the box blue and we used white for the letters. And I think it turned out very nicely. Every letter is its separate component. Let's fast forward. Just turn off the front here so we see something. Okay, yeah, now we have the screws. So this is for us to connect the two pieces. Let me just open the side view again. And let me turn on the front. So the front also has a piece of plastic that is attached to it, and it has a place for the nuts to go in and a place for the bolts to actually connect to the nuts. And then you can't open the box once it's screwed into place. But it can easily be removed in a few seconds with a power tool. So let's skip again a few steps. I think that's more or less it. All these things that you see here are built for tolerances, so pay attention to this. When I go back, this has no space in between. So basically, when we cut a body in Fusion 360, it basically just makes one atom of space between the bodies. But when you print it out in the real world, that's not enough, and it can't actually close. So that's why we have to account for tolerances, and this is just me playing around with the tolerances. So this tolerance is good for us to have a nice strong seal, but also for it to be easily opened when needed. And I think that's more or less it. Yeah, now we reached the end. Just a second. Let me show this body. Yeah, and the last body I just pasted, I used something that was already available on the internet, a mechanism for connecting two pieces, and we just basically glued these together and it works nicely. And it's all printed as one piece. Okay, that's for Fusion 360. Just a second. So once we have everything we need in Fusion 360, then comes the part where we actually export that file and get it ready for the 3D printer. And for that, we actually need something that's called slicing software, and I'll demo that now. Just a second. Okay, so let's say that we just want to print the front of the case. Let me just close all the other bodies here. So all of these, there are a lot of bodies. And now we just have, I can also close the bolts and the Raspberry Pi, which is above. So now we just have this, and I can close this. And let's say we just want to print this. Then we select the whole thing, and then we just go to Utilities and Make, and get it ready for 3D printing. That looks good. Now this will open the Prusa Slicer software. So let's hit OK, and Prusa should open now. It's opening. It's importing, and now it's here. So there we have the 3D model that's ready for printing. So what does it mean for things to be optimized design-wise for 3D printing? I cannot just print this like this because how 3D printers work, they always need to have a bottom layer. So I cannot print this without there being anything between the build plate and this plastic here above. So that's why I chose to print this on its side, like so. And now everything has something underneath it, and it can print nicely. And now if I just click Slice Now, these are just some settings for the printer, how thick we want it to be, if we want it to be 100% plastic. But if we put just 15%, it optimizes for strength, but also we use less material and less time. So if I just click Slice Now, it will do some calculations. And now we see why this software is called slicing software, because everything is basically just sliced into layers. And I'll demonstrate that now, just a second. So yeah, everything here is a layer. And now you can see what I mean by not filling it up completely. You see this is not 100% filled up, but it's also very strong. And yeah, a 3D printer basically goes from the bottom layer and gradually prints out the whole piece until it's done. This Prusa Slicer software is free, and in my opinion, it's the best one out there currently. It's made by the same company that made my 3D printer, so I'll get into that now. Let me go back to the presentation. Just a second. So this is my 3D printer. It's a Prusa Mini Plus. It's a $450 printer, and again, I used PETG plastic for the 9-air case. And now in the next slide, we have a time-lapse video of how it printed out the two main pieces, the back and the front, and you can see side by side. And yeah, that's basically it. I basically repeated that process 7 times until we got all the boxes that we needed. And the quality of the video time lapses can be even better, but we didn't have access to a higher quality camera, so we just use an HD webcam, and this is the result. Okay, moving on to the next slide. So this is how our assembly process looked. After all the boxes were printed, we glued all the letters in place, all the nuts in place, and we glued the bug screens so bugs can't get in. And yeah, basically that's it. We also put in the sensors and connected the two pieces, and yeah, they were ready. So now we get into the part of what you would need in order to create your own. So of course, you would need access to the 3D models. I have a QR code in one of the next slides, and you can access that repository and download all the models. Of course, you need access to a 3D printer. We used two colors of PETG plastic, blue for the case and white for the letters, but also white for prototyping, since the white letters are a small percentage of the filament. So we just kind of save material. That's why this prototype box is white. And I just used some other color that I had around to test how the letters fit into place. So besides that, you need the Prusa slicer, you need two M5 nuts, two M5 25 millimeter flathead screws. So why flathead screws? Because basically that's what we had on hand. And if I turn on the back one, they go nice and flush on the back of the case, like so. And that's also good if you're mounting it to a wall. Basically, you can't see the nuts if they're flush against this surface. Next, we need some smaller screws, M2.5. Those are for the Raspberry Pi. We need a paper clip, and a paper clip is used for the smallest sensor, which is the humidity and temperature sensor. So let me just show that off real quick. So once you put the sensor here in its place, you can use a paper clip to connect it with the back here, just by going through these holes. Next up, we have the window screen that's used for the bugs, a hot glue gun to glue it in place, and super glue for the letters. And basically that's more or less it from everything that you would need. Now we move towards the end of the presentation. One of the next presentations will be from our colleagues Vuk, Igor, and Miro. So that presentation is gathering, processing, and displaying air quality data in the cloud. And next, after that, we have enhancing the power of AWS cloud solutions for a worldwide problem. And for the end, we have empower your team to innovate with Azure while tackling the present. As I mentioned, here is the QR code and the link where you can download the 3D models. I can actually demo that here. I think I have it open. So this is the site. I think you see it, right? So here we have all the files that you would need, and you can just download them. And even GitHub supports viewing STL files before you download, so you know what you're downloading. So this is the back case. Going back to PowerPoint. Yeah, now we move into the Q&A section. If you have any questions. Anybody?
I can see everyone is impressed.
Yeah, it's really obvious that you guys had a lot of fun preparing this. I have one question. So what was the most challenging part of this process for you?
The most challenging thing I would say is this thing here for me. So if I zoom into this, so this is the bottom part and this is the upper part. It's kind of ugly because I used a new design approach when I created the back thing, and then later it didn't want to play well with the front of the case just because of a function. Then I was playing around with making this look pretty but also functional. This piece right here gave me the most trouble, so it's not something you would expect, but yeah. With every project, you learn something new in the software, and then you want to try out that new thing, and then sometimes it gives you problems like this gave me. But more or less, this is a really simple design. It wasn't really challenging to do. I've designed a much more complex things, so I'm happy that I could help out the team with this. Thank you, Nina, for your question. I think we have a question in chat. I almost missed that. How long did it take to learn Autodesk Fusion 360 and to create the model? How precise is it? I'm not sure what this how precise means, but to learn Autodesk Fusion 360, it's kind of an ongoing process. The basics you can learn very quickly because the software itself is really nice and easy to use. You have all of these tools here and you can play around with what they do. And the good thing is, once you know just a few simple things, then you tend to think of a lot of ways of how to use the tools that you know. That might not be the best approach. For instance, let's say if I go back, let me just, I don't want to go back. So if you remember, there was first just this one circle here, and then it was all of the 9. So what you could do is draw each circle by itself. And if something changes, then you have to edit all of them. But if you just draw one and then you just use like a rectangular repeating tool, that creates all of the ones that you need. And if you need to edit anything, you just edit the one and all of the other ones automatically adjust. So it's just, you can do it by drawing. There's nothing wrong with that. But once you learn more tools, you become kind of more advanced. But in order to get started, it's very easy. And you can build basic things with it pretty quickly. I hope that answers the first part of the question, but again, for the how precise is it, I'm not sure what you mean. Rate of expected to actual size. Well, it's really precise because all of the sketches, let me just go into, let's say the first one, the most basic one. So it starts with a sketch, right? And if I go into the sketch, these are all just dimensions, so 140 millimeters, 70 millimeters. So it's really precise because you're working with actual real sizes, so it translates really well. So everything I had to do, I had to measure it, account for tolerances, and then it was all just pretty precise. Hope that answers your question. Okay. Anything else? No problem. I guess there are no more questions, and then I would just like to thank you all for your time. And yeah, we made an umbrella for our sensor in Novi Sad for the heat. I thought it was just cute and I wanted to include it in this slide.
Great work, guys.
Great presentation. Thank you, Stefan.
Yeah, thank you. Thank you.
Thank you. See you.
See you. Bye.
Okay.
Bye
Thank
bye.
you. See you.
Bye.
See you. Bye
Bye-bye.
bye.
Bye.
Bye.